So let's start with one of our first counting or combinatorial principles, and this is what we sometimes call the addition principle for disjoint unions. So what the addition principle for disjoint unions asks us to consider is two sets that have no overlap. So here's our setup. Let A and B be two sets with the property that their intersection is equal to the empty set. There's no elements that are in both of them. If I have two sets like this, we have a fancy word for this. They're called disjoint, no overlap. And there's a kind of intuitive picture here of two disjoint sets. So here's my universal set in gray. Here's A, here's B, and in the Venn diagram, they have no overlap. There's no overlap between them. So if I ask myself, hey, what's the cardinality of the entire green area here, so all of the shading here and all of the shading here, what I'm asking about is the cardinality of A union B. That's all of the green area. And in this picture, what we can see is, hey, if I want to know the green area, then it visually looks like I can just add together the area of A and the area of B. And this is indeed what the addition principle says. So here's the theorem. If A and B are disjoint, and this is important, if they're not disjoint, this doesn't work. We'll see what to do in that case later. If A and B are disjoint, then the cardinality of A union B is equal to the cardinality of A plus the cardinality of B. This is very useful in a lot of cases where we're considering an OR type of problem. We'll see lots of examples of this. If I'm going to pick an element from set A or an element from set B, that's the same as picking an element from their union. So when I say, hey, I want to pick something from set A or from set B, if set A and B are disjoint, then the number of ways for me to do this is just the size of A plus the size of B. So let's look at an example. Here I want to know, hey, how many integers, n, are there between 20 inclusive and 30 not inclusive? So I'm talking about 20 through 29. How many integers are either prime or even? How many integers are either prime or even? So the key thing to note here is that, hey, any integer larger than 2 cannot be both even and prime. So what I am going to do, I'm going to use this observation. Hey, the prime numbers larger than 2 are always odd. That's just the fact I'm using here. So this means I'm going to define two sets. So let's define A to be the set of prime numbers. So x is an integer such that x is prime, and 20 is less than x, which is strictly less than 30. I'm going to define that set. That's my set of primes. And I'll define another set. This is going to be my set of even numbers, x in the integers with the property that x is even, and x is and the property that x is greater than or equal to 20 and strictly less than 30. So here, the way I'm going to use my observation that any integer larger than 2 can't be both even and prime, what that says is that A and B are disjoint. A and B are disjoint. There is no integer that is greater than or equal to 20 and both prime and even. So this means that if we want to calculate what the question is asking us, so this is an or kind of question, either or. So either or means I need to consider a union. So if I ask myself, hey, what's the size of A union B, I can apply the addition principle for disjoint unions. It's A size of A plus size of B. And so I just need to know what those sizes are. What's the size of A and what's the size of B? So I can check, okay, the size of A is the set of primes between 20 and 30. And that set, what A is, it includes 23 and 29. Those are the only primes between 20 and 30. And then the size of B, well, that is the set 20, 22, 24, 26, 28. Notice that we can kind of see the disjointness when we write out in roster notation because there's no number that's in both set A and set B. So let's check here. Okay, so the size of A is equal to 2, and the size of B is equal to 5. And so my disjoint union calculation says, hey, the size of the union of A and B, that's the set of all integers that are greater than or equal to 20 and strictly less than 30. The size of that set is equal to the size of A plus the size of B. The size of A is 2, the size of B is 5, and therefore the size of that set is 7. There are 7 integers between 20 inclusive and 30 exclusive that are either prime or even. So this is our first example of using an addition principle in order to solve an OR type of problem. Okay, so wait. Disjoint unions are all well and good, but often we have cases in which we want to calculate the size of the union of two sets, but the sets are not disjoint. So in this kind of scenario, we actually need to go back to an old friend, the inclusion-exclusion principle. So what the inclusion-exclusion principle says is that if my sets are not disjoint, then I can do the same thing. A union B, its size is equal to A plus A size of A plus size of P. That part's familiar. But I have to add a correction term. I have to add this correction. A intersect B, I have to check the size of that set, A intersect B. And the reason that I have to do this is that this fixes some double counting. So this is fixes double counting of this intersection A intersection B. The reason why I'm at risk of double counting is that there's one copy of A intersect B in A and another copy in B, and so I don't want to count it twice. So let's go ahead and just jump straight into an example of using this inclusion-exclusion principle. So let's do an example with counting integers again. So here's my question. How many non-negative integers between 0 and 60 inclusive are multiples of either 3 or 4? Now, the reason we have to use inclusion-exclusion here is that some numbers, for example, 24, are multiples of both 3 and 4. And so I need to consider elements that satisfy both of these criteria, not just one. So here's our approach. I'm going to make a definition here. Let S sub I be the set of multiples of I that are between 0 and 60. And we need that X is a multiple of I. So this is a flexible definition. I'm going to reuse it multiple times. Then let's take a look at what S3 and S4 look like. So to start off, S3, okay, what is that set? Let's take a look at it in roster notation. It's all of the multiples of 3. So that's going to be 0, 3, 6, and so on. And I'm going up to 60, and so my last couple of elements are going to be 57 and 60. Of course, sets don't really have last elements, but this helps me to remember what should be in there. And if I want to know how big this set is, so let's look at the cardinality. Well, I have 60 divided by 3 is a pretty good way to think about this. That would give me an answer of 20. I need to also factor in the 0 here. And so the total number of things in here, which you can count if you're feeling moved to, is going to be 21. elements of S3. Now, if we look at S4, so the set S4 contains all the multiples of 4, so it's going to look pretty similar. 0, 4, 8, and so on, up to 56 and 60. Here, similarly, the size of set 4, it's going to be 15, which is 60 divided by 4 plus 1 to account for 0. So the size of S4 is going to be 16. And you'll already notice that these sets are not disjoint. So I have a 0 that's in both of them. I have a 60 that's in both of them. And what we want to do is figure out how to compute the size of S3 union S4. That's what our problem is asking us to do. How many non-negative integers are multiples of either 3 or 4? However, because our sets are not disjoint, we need to figure out how to also calculate the size of the intersection. And our key idea here is that, okay, what is S3 intersect S4? Well, it's the set of all numbers which are multiples of both 3 and 4. And because 3 and 4 have no common factors, this set is actually a set that is kind of familiar in a way. It's S sub 3 times 4, or alternatively S12, the set of all multiples of 12. What is this set? Well, the set of all multiples of 12, it's 0, 12, this one is smaller, so I'll just write out the whole thing, 24, 36, 48, and 60, which means that the size of the intersection here, how many elements did I write down? There were 6 in total, the size is 6. So now I have all the ingredients that I need for my solution. So the size of this intersection, or the size of the union, sorry, is equal to the size of S3 plus the size of S4 minus the size of S3 intersect S4, which is equal to 21 plus 16 minus 6, which gives us a total of 31. So even if my sets are not disjoint, I can still use a version of the addition principle. I just need to make a correction for double counting of the intersection using the inclusion-exclusion principle.